Hello, it's Lee. I'm back in the lab. The lab here is toasty warm, back in the basement, 5 degrees. So I'm not going there for a little while. What I have to show you now is very interesting. I'm going to tear down and analyze the contents of this Harvard Engineering MagNode. This is part of a sort of predecessor to the Internet of Things that's been installed on lampposts all across the world, and it lets your local council or authority, your local jurisdiction, have more control over the street lighting and more feedback about what it's doing than you ever have with the old time switches or the photocells on top. So let's take it apart and see what makes it tick. Okay, so reverse engineering is complete, and I can now take you through what makes this thing work. Let's start by just laying out these bits here, and where is my, here we are. What we need here is a bit of a block diagram to get us going, because it's 3 boards, it's quite a complex system, and I thought it'd be easy just to talk through these boards one at a time. If I can find the missing processing board, which has vanished. Nope, it's disappeared. Oh, here it is, there. One processing board. So there's 3 boards in here, and you can see those on the device here. This is the one that's still in one piece. The lower board here is the power and power control board. Then here we have a little sort of CPU processing board, and on top is the antenna board with the RF chip and RF transceiver inside it. So I've drawn these out in a bit of a block diagram here, just to make it a bit easier to see how they all interact with each other. Normally, as you saw in the device that's still in one piece, these are stacked up a bit like that, and all the connectors on the bottom here mate with the other boards. When I had this original one here, I tried to prise it apart really carefully, but because the whole thing is covered in this conformal coating, it covered all the connectors as well, and they wouldn't come apart at all. So the whole thing just fell to bits, and all the tracks came off the circuit board when I tried to take it apart, just to get the antenna off here so I can run some antenna tests. So I bought a new one on eBay, so we can now, in a previous video, you can see how it works and actually see it in operation. But the layout here of the 3 boards, there's the power board here, that controls CPU board, and the RF board. The power board has 2 components. One is it supplies power via these 2 capacitors as a capacitive dropper into the control board here. And the second thing it does is, of course, to switch on and off the light that it's installed on. Now, I've done a full reverse engineer of this board. I'm not going to do that on these boards here. I've done a bit of investigation into them, but they're quite complex. They're multi-layer boards, and it'll take a long time to properly reverse engineer those. And really, it isn't necessary, because you can look at the large components and work out what they're all doing without that level of reverse engineering. So looking at this board here, this is the power control board, and I've drawn out the circuit diagram of this board here. And it's quite simple. So we have here the live and neutral coming into the board, and this red here is the live switched out, which goes to the light fitting on the street light, which is going to be turned on and off by this device. Now you can see here on the board there is a live in, a neutral, and a live out here. So as well as having these cables coming into the board, you can also fit it with one of the connectors that will connect directly into the top of one of the lampposts. So rather than having to take the lamppost apart and drill a hole in the top, if the lamppost has one of the old light sensors in one of the photocells, that will clip off, and it's got a little socket on the bottom, and then you can plug this back into it as a direct replacement. That makes fitting and installing these really, really easy. Why they have some with these cables on, I'm not entirely sure. Maybe there are some lampposts that can't be retrofitted like that because they haven't got the photocell on the top. But the one I have here has the cabling in. So the first thing you see with the neutral supply here and the live supply coming in is there is this class X capacitor across the supply here, and that stops some transients and stops interference going up into the device and back down into the mains cabling. Let's start with the neutral supply line here. This is very simple. It only does two things. The first thing the neutral does is it goes via these two capacitors here, which are in parallel, and they were here and here on the board, and then through this choke, and that supplies the power to the processing board here, the power supply side of the processing board, which converts that into 3 volt, which is what the rest of the system runs on. The live side is a bit more interesting. So the live comes in here from the brown cable or from your plug, and the first thing it hits is this shunt, and all a shunt is a little loop of cable here which carries the main current, and the purpose of that is that if you measure the voltage across that shunt, then you can use that voltage to derive how much power is being drawn by the light. So in a previous video, the one before this video, when you saw me using this device here to actually connect and control the Harvard LeafNUT here wirelessly, at the end of the testing with this device, you could see the voltage on the line and how much power was being drawn. And the power draw, which is the power of our test light, was measured via this shunt here. In the next stage of the main supply to the live out is the switching section. And the switching section consists of 2 ways of switching the light on and off. The first is this relay here, and the second is this triac. So both of these devices are functionally identical. They both switch the power on and switch the power off. But the reason there's 2 of them is because they complement each other and they make the device last longer. Relays are great. They are mechanical switches. Inside a relay there is a coil of wire like this there, and inside the wire there's normally a solenoid device, and then up here there is a contact, and there's a contact here like that. So what will happen roughly is when you apply power to the solenoid, it ejects that core there, it pushes that up to the other contact, and that makes contact, and the relay is then passing current through the switch and the device is turned on. Other relays will just have a coil like this, fairly solid coil. They'll have a contact here, and then the other contact will be moving towards or away from there like that, based on whether or not the coil is energized or not. This relay is slightly more complex because it is a latching relay. So with these normal relays, you have to have the coil energized all the time for it to be turned on. The latch relay works by energizing the coil once in one polarity, and that turns it on, and then when you reverse the polarity, it turns it off again. So you haven't got to have current flowing to the relay all the time to have the light turned on. And that's good because that again prolongs the life of the relay. The triac is essentially the electronic version of the relay, and when you apply power to that pin there, the triac, to the gate pin, it will start conducting in both ways through the device. And then when that is brought lower, with reference to A1 here, the gate A1 reference, then it turns itself off again. The reason we have 2 of these here is because these light fittings that might be installed in street lights, they could be LED fittings, they could be pressurized sodium lamps, they could be halogen lighting. A lot of these lights can take quite a high inrush current. So the current that goes in when you start a device up can be maybe 10, even 20 times greater than what the device normally pulls. So a 5 watt light, for example, I had one here, it's vanished. A 5 watt light might draw 50 or 100 watts for probably less than a millisecond when you turn it on, and then that current reduces back down to what it should be and what the normal operating current is. Now when you have a relay contact, what will happen is that the contacts will make like that when it's turned on, but just when they almost touch each other, there'll be some arcing and some sparking between the contacts, and that damages the contacts. What it does is it pits the contacts, makes little holes in the contacts, and makes them rough rather than being smooth. And eventually that wears down so much that it degrades, so it won't actually make contact anymore. Or there's a high resistance here that can cause other faults. You can get hot, you get more arcing, or you have reduced power to the light fitting. And that can happen relatively quickly, even with quite large, quite big relays, depending on the current being pulled. Whereas this device here, when it switches on, there's no moving parts, and so there is no surface of a contact which is going to suffer from this pitting here. So why not just use one of these, you might ask? The problem is with a triac is when it's passing current, it's going to lose some current on the way, and it's going to start to get hot. And this is just placed on here like this. It has no heatsink. All that excess heat is nowhere to go, and it will end up failing relatively quickly if there's a higher load on there. So what they've done, and this is what's called a hybrid switching triac relay arrangement, and it's quite popular in devices that you actually want to last for more than a few years, is when power is applied here, it charges up this capacitor, which is the one here, and because there's not enough current and not enough voltage flowing through the circuit to energize the relay immediately, the first thing that gets turned on is this triac. So the triac starts passing current just a few milliseconds before the relay engages, and the relay then starts taking the load. And then to turn it off again, the polarity to the relay is reversed, the contact in the relay de-energizes, and the triac also, because that then the gate is then on lower in reference to A1, the triac also disengages and the circuit is broken. So that essentially is how that works, and there's not much more to the mains board here. It's quite possible that the voltages here and the way it's applied to the coil and the triac is not exactly as I described, because I haven't had a chance to test that yet, which I might do later and do a demo on the bench here to show you how it works. What I have done is I've just attached a capacitor to a relay here so I can time how long a delay it provides to the relay. It's very short. It's in the region, I'd say, of 10 to 20 milliseconds, although I just guessed that, so that's hardly a scientific reading, but it definitely sounded a bit slower than when the voltage was applied directly. The other boards are a bit more complex. What I've done, in order to identify these chips here, I had to soak the boards in some alcohol like this, and then the conformal coating which covered all the chips over and made the device identifiers pretty much unreadable was easy to wipe off. So that's all been wiped off now of the devices on here, and so we can have a look at the devices and see what they all are. What I've done is I've taken some photos of the boards here, and we can use those because I've written on the devices and what they all do, just to make things a bit easier for us. So we'll start with the bottom side of this control board here. This is essentially just a power supply. It's a buck regulator, and it's controlled by this chip here, which is a 33063, a very popular buck boost regulator found in lots of power supplies. In fact, I think the power supply here I was looking at the other day, no, not that one, that's an even cheaper one, but I had a power supply in bits the other day, and it has the exact same chip in it, so these are very popular. The other chip in here is a MOSFET, which is part of the buck regulator here, but the whole device here, the whole side of the board here, its sole purpose is to convert the power supplied from the power board here via those capacitors into 3 volts, because all the other devices here and on the RF board are 3 volt powered devices. So the whole side here is just a power supply. Flip the board over, this is where it gets a bit more interesting. This is the processing and control side of the board, and we have 3 devices here that are of note and interest. The first device here on the left hand side is an op-amp, and that is being used to measure the voltage across that shunt in order to derive our current usage of the light that this is connected to. the other two devices here, the two large black ones here, they are actually both microcontrollers. I was quite surprised to find that it had two microcontrollers on here. I'm not entirely sure why I would have two there. It could be because there's not enough I/O pins on here, or maybe some other issue with this device prevented them from using it. But the device here, the 7F Lite 02WP, is an 8-bit microcontroller unit, and its sole purpose, by tracing some of the connections here, is to connect to the op-amp, and it connects to a voltage divider via a couple of analog digital converters built into the chip, and all it appears to be doing is measuring the voltage to the lamp and measuring the current, and it also turns the relay on and off. So that's all that device does there. It's essentially the control chip for the power board, which we saw just now. This one here, the larger one, that is a PIC 18F25 microcontroller device. It's a bit more capable. Again, I mean, these are very, very low power CPUs. You're talking about pocket calculator kind of power here, but that's all it needs to do. It's just turning lights on and off and talking across a wireless network. These two devices are joined via a I2C serial connection, and then this device here, this CPU here, talks to this device here. This is the RF board via another serial connection, and you can see that serial connection over here. So the RF board is, I think it's a bit more interesting. It has three components of note. I'll just pull down the image for the RF board. So on the RF board we have these three components here. This one, the one here, and that chip there. The one to the left hand side is a 2 megabit flash EEPROM. That is just some memory where it will store configuration parameters, maybe software updates for this device, and potentially even for the device on the control board as well, for that microcontroller there as well. The second chip here is this SI1000 general purpose RF chip. This is a really interesting chip here, and I'm going to put all the data sheets for all of these in the comments and description down below in the video, so have a look at those. This one is a 300-page manual, because this is actually a very, very capable little chip. It is essentially a very basic software-defined radio inside here, an 8088 microcontroller, and plenty of I/O, so we can talk off to things like the EEPROM here, and back down to our control PCB here. Distinguishing features of this chip: it's got a max output of 100 milliwatts, although I believe the recommendation is that you don't leave it transmitting at 100 milliwatts for very long, because it's going to overheat and possibly fry itself. But it's also very sensitive, so it can receive signals reliably down to about minus 140 dB, which is really, really very, very good indeed. The other component of note is this here. This is a RF switch, and the RF switch is here because the SI1000 transceiver has two antenna connections, one for the transmit antenna and one for the receive antenna. So the RF switch here will switch between transmit and receive depending on what that device is doing, if it's transmitting or receiving. And that connects to the antenna, which is up here. So that is essentially it. On the block diagram here, you can see all these components. As I said, I'm not going to dig down and reverse engineer the entire details of this device here, or of a device here, especially this one, because this appears to mirror the reference design on the SI datasheet. So there's not much point in tearing that down at all, because that's already available. And this is just a couple of microcontrollers, that op-amp there, and on the other side you have the power supply, which supplies 3 volts. So yeah, that is essentially it. It is a 3 boards. You have the RF board here, the board with a couple of CPUs on and power supply, and at the bottom you have the power board, which does the switching on and off of the power to the light into which this is installed. one other quick thing to have a look at is the antenna here. This antenna here I've actually cleaned off using some solvent so I could test the antenna with the conformal coating on and conformal coating off, because there's claims that, and it sounds daft even saying it, that the little blob of resin at the end, blob of conformal coating, is a dielectric lens. So I tested it with the coating on and with it off, and found in a previous video that the antenna response is identical. But the one here still has the coating on, and this has been quite impressively done. So the way they dip these in coating is that they hold it by the wires here, and they just dunk it in and they hang it up to dry. So you can see that the whole thing is covered in conformal coating, including some of the wires here. There's a bit here on the wire, and it goes up the wire here. But what they've done as well is there's lots of little blobs all over the circuit board here. So there's a big blob here. You can see that there's a blob of it here. There's a blob of it here, and there's a blob of it down here, and it's all over the place. There's a huge blob on the relay here, but that just sort of shows that the blob on the end is not, as claimed, some kind of crazy dielectric lens antenna, because a dielectric lens at this frequency, which is 869 megahertz, would be very, very big. And I'll put a link to a video that Andrew McNeil did. He has a great channel about antennas where he describes what the dielectric lens for this frequency would look like, and it's very big. This originally had that little blob on the end there, which you can just about see. It fell off when I was playing with it earlier, but that was on the end there, and you can see that all that happened is that it was stuck into the conformal coating, and it ran down the antenna and formed a drop at the end. And Mark Steele thinks that that little drop of conformal coating at the end of the antenna is a dielectric lens. Yes, it is not. So there we are. If you want to look at this device actually working and being controlled over the air with the control box I have, this one here, then there's another video. It is just a demo of me using this control box to control this device remotely and turn the lights on and off, but it is quite interesting. And there's lots of other videos with testing the antenna on this device just to see what the performance of the antenna is. It is, of course, a quarter wave ground plane monopole, and it is omnidirectional. So there we are. That is inside a Harvard Engineering magnode, which might be on a lamppost near you. There are lots of comments down in the description with all the links to the data sheets, and I'll also try and get some close-up photos if I can and put those on as well. So if you want to, you can zoom in and reverse engineer this for yourself. Be warned, these are at least 3-layer boards here, although the power supply board is 2-layer. These are 3-layer boards, and so trying to look inside the board to reverse engineer it inside is going to be impossible. However, if you'd like to own one of these, if you go on to eBay and just search for LeafNUT, they are $8.99, and I believe that the person selling them has quite a lot left. So if you're interested, hop on eBay, buy one for yourself, and join the LeafNUT club.